So, uh, the I'm going to discuss coordination chemistry questions over here. So, coordination chemistry is a very important topic as far as CSI NET is concerned, and the some of the important like topics from this chapter are magnetic moment, term symbols, and orbital diagram, and the charge the spectra, color and spectra basically. Okay, so I'm going to cover some of the questions in general questions, not specific topic based. Okay, so this is the first question. Determine the hybridization of cobalt cyno 6 4 minus this complex. We have to determine the hybridization of this complex. Okay, so these are the options that are given. So now we can see that cobalt is in the +2 oxidation state. You can see that X minus 6 if you do is equal to minus 4. That is, you get cobalt is in the +2 oxidation state, and the configuration of cobalt is 3d7, cobalt 2 plus. Otherwise, its configuration is 4s2, 3d7. Two electrons have been removed, so we get 3d7. So as Cn minus is a strong field ligand, basically a strong field ligand is that is we denote them on the basis of spectrochemical series, the strong field ligands and the weak field ligands, based on the splitting, the crystal field splitting, how much the gap between the T2G and the EG level. Okay, so the as Cn minus is a strong field ligand, it causes pairing of electrons, and the d orbital has 3 pairs of electrons. You can see here, you will understand more. Yeah, from this. Now, cobalt, if we consider simple cobalt, it is 3d7 4s2. Okay, two electrons have been removed. Then two electrons have been removed from the 4s2, and this is the configuration that we get 3d7. Now what happens is, as Cn minus is a strong field ligand, it pairs up these two electrons. Now these two electrons have been paired up, and we have one electron here which is left. And this electron, it can be transferred to the 4d orbital. This single electron, it can be transferred to the 4d orbital. Why? Because the cobalt 3 plus, it is more stable as compared to the cobalt 2 plus. This how cobalt 3 plus can be obtained? When we this I'll just say, yeah, you can read it. The d orbital has three pairs of electrons. One electron is unpaired and is transferred to the 4d orbital. This extra electron is present away from the nuclear pull and can be removed easily, making this complex a good reducing agent. So it can reduce the other species and it can oxidize itself. So the oxidation state of the cobalt 3 plus after the removal of the that electron which is present in the 4d is cobalt 3 plus, obtained after the loss of the electron, is more stable than cobalt 2 plus. Okay, so now you can see that these orbitals are empty. These two d orbitals, this 4s orbital and three p orbitals, these are empty. And now the Cn minus ligand, the Cn minus, it can donate the electrons in this, and the configuration that we get is D2sp3. This is the configuration that we get. Okay. So if we move on to the next question, um, now we need to find the CFSE of this complex. Okay. So cobalt is in +3 oxidation state. Now you have to see this fact that cobalt 3 plus with H2O. Cobalt 3 plus with H2O, it acts as a H2O acts as a strong field ligand here. However, it is weak field, but with the cobalt 3 plus, it acts as a strong field ligand. And there are a few ligands which act as a weak field ligand with cobalt 3 plus, which are like the halide ions, you can say, and the N3 minus, S2 minus. They act as a weak field ligand with the cobalt 3 plus, only some of them, while H2O acts as a strong field ligand, and hence it will cause pairing. So you can see that cobalt 3 plus has a configuration of 3d6. How? Because it was 4s2 3d7, and after the removal of 3 electrons, we get 3d6. Okay. So H2O behaves as a strong field ligand with cobalt 3 plus. This complex is low spin with the configuration of T2G6 and EG0. Here you can see that this is the splitting. Now, since it is acting as a strong field ligand, this delta naught, the crystal field stabilization energy, this is going to be high, and the gap between the EG and T2G is going to be high, right? So now, according to VBT, you can see the valence bond theory. I'm not write it. Sorry. According to VBT, you can see that if we fill the 6 electrons, 1, 2, 3, 4, 5, and sixth electron is here. Now, all the electrons, they have been singly occupied. First, the 5 electrons, and the sixth one is getting. Now we have to fill the sixth one. Is here only, sixth one. Okay. So now we need to see the CFSE. How do we calculate the CFSE? So CFSE is calculated basically based on this. This is the barycenter that we get, and this lower part, this one is minus zero point 0.4. This one is minus zero point 0.4 delta naught, and this the higher one is this one between the above the barycenter. It is plus zero point 0.6, right? So why minus zero point 0.4? Because the T2G, they are getting stabilized, and that is why the minus zero point 0.4 delta naught, and EG are getting destabilized. So how do we get the EG and T2G? Basically, the ligands that are these two orbitals are dz square and dx square minus y square, and these are dxz, yz, and xy. So the ligands are approaching directly towards these two orbitals, and that is why its energy is high. while the ligands are not approaching directly, as these the X, Y, Y, Z, they are present in between the axis, right? So, okay, so if we calculate the CFSC, so it will be minus zero point 0.4 into 6, 6 electrons are there, you can see, and plus 0 into zero point 0.6. Here, no electrons are there, so we put 0, delta naught plus 2p. Okay, so how do we get this 2p? Now, this is very important. This kind of such questions, they have been asked in CSIR NET and GATE also. So you have to see this carefully, that uh, you'll count 2p and not 3p. Why? See, because this you'll not count as because of pairing. These two have been paired. These two have been paired. This electron has been paired with this, and this one with this, and you'll not count this pair. Okay, this has not been paired up by the strong field ligand. Okay, so you will count 2p and not 3p. You will not consider 3p, because we have to fill one electron here, because all of them have been singly occupied, and one we have to fill here. That is why. Okay, so only two pairing have been done, and that is why we get 2p. So this is what the CFSC that we get, minus 2.4 del O plus 2p. So this is your answer, D. Okay. Now, this is another question. As a spinals, basically, spinal is not very important from the CSI NET point of view, but it is important for the GATE exam, because every year, almost every year, GATE in GATE exam there are questions based on spinals. Okay, so we need to see what is a spinal. So spinal is basically, it is A, B, 2, and O, 4. This is what we get. Okay. Now this is a general formula of a spinel. So A has a oxidation state of plus 2, while B has an oxidation state of plus 3. So there is a criteria for the normal spinal and the inverse spinal. First, we'll see the question. Okay. Now we have to find the CFSC in the octahedral field. Because we have CO3O4, we'll consider A also CO. We'll not consider, it is there itself. CO will be A, and B also will be CO2O4. Okay, the cobalt. So cobalt is in the plus 2 oxidation state. It will be 3d7, 4s2, 3d7. 2 electrons have been removed, we get 3d7. So the configuration will be T2G5, Eg2. Okay, this is how we'll put the electrons. This O oxo, and here you have to see that O2 minus, which is present here, O2 minus, it is present in the lattice points. Okay, O2 minus is present in the lattice points, and A and B are present in the voids. These A, the cobalt is present in the void, and O2 minus is present in the lattice points. Okay, so T2G5 and Eg2. So again, we are going to do that, the crystal field stabilization energy in the octahedral field. So we will multiply. And now one more thing you have to note, that CO2 plus is given and O2 minus. It is going to act as a weak field ligand, right? Simple weak field ligand, this oxo, it is a weak field ligand itself, and with cobalt 2 plus, it will be weak field. So each of the orbitals will be singly filled first, the T2G and the Eg, and then the pairing is going to take place. Okay. So 1, 2, 3, you can see here. I'll just, yeah, if we take, no, I'll draw it over here. Okay. So, we'll fill 3 electrons, 1, 2, 3, and 4, 5, and the 6, 7, like this. Okay. So now minus zero point 0.4 into 5, 5 electrons in the T2G, plus 0.6 into 2, and del O, and this is what we get. This is the value. Okay. Now in cobalt 3 plus, you have to see. With cobalt 3 plus, O2 minus will act as a strong field ligand. I mentioned this, that only some of the ligands, like the halide ions, N3 minus, SCN minus, S2 minus, they act as a weak field ligand. Only these oxo, this ligand acts as a strong field ligand, and therefore it is going to pair up the electrons, and we get 3d6, T2G6. All the electrons will paired up in this T2G, and we get it. So minus zero point 0.4 into 6 del O, so minus 2.4 del O. Okay. So you can see here O2 minus behaves as a strong field ligand with cobalt 3 plus. Okay. Now we can see that the CFSC of cobalt 3 plus is greater than minus minus zero point 0.8. Okay, this is greater. This CFSC is greater than this. So we can say that it is a normal spinel. So what is the criteria of a normal spinel? That the A is present in the tetrahedral voids while B is present in the octahedral voids. Okay, and if the CFSC of B, which is cobalt 3 plus, is greater than A, which is cobalt 2 plus, so then we get a normal spinel. Okay, so since the CFSC of cobalt 3 plus is greater than cobalt 2 plus, it is a normal spinel. So this is a normal spinel. And for the inverse spinel, the CFSC of this A2 plus becomes greater than the B3 plus. Okay. So next question we'll see. Okay. So the complexes of nickel, these two complexes of nickel have been given. So we need to find out whether they are paramagnetic or diamagnetic. Now you can see that in both the complexes, nickel is in the +2 oxidation state. Okay, having a configuration of 3d8. It has a configuration of 4s2 3d8 valence configuration, and after removal of 2 electrons, we get 3d8. Now Cn minus is a strong field ligand, while Cl minus is a weak field ligand from the spectrochemical series. So nickel tetra, this complex, nickel complex, is a square planar complex, and it has a diamagnetic nature. So this the square planar, we have to remember this, that nickel 2 plus, you have to remember this, that nickel 2 plus uh, with the strong field ligand, it is going to give a square planar complex, and it will be having a diamagnetic nature. While the with the weak field ligands, it will be a tetrahedral complex having a paramagnetic nature. You have to remember this for the uh, with this strong field, you have to see the ligand, the nature of the ligand basically, whether it is a strong field. When it will be a strong field ligand, always there will be with the, I am talking about D8 only. I am not talking about other configurations. I'm talking about D8, that nickel is in D8 configuration, having a square planar complex, then it will be diamagnetic always. While with the weak field ligand, it will be a tetrahedral complex with a paramagnetic nature. So you can see this. This C will be the right answer for this. Now, yeah, this question is important. You can see that assign the acidity order of the following aqua complexes. Okay. Now we need to assign the acidity of these complexes. Now you can see that iron is in the +2 oxidation state, nickel in +2, iron in +3, and mercury in +2. Okay. Now you can see that the higher the positive charge and smaller the size of the metal, higher the acidic character of the aqua complex. So higher the positive charge and smaller the size of the metal. Okay, so you have seen that higher charge. This has higher charge than all of these three. A, B, D, C has the highest charge, right? But you have to see other important thing as well, which is this one. So in the complex, this mercury complex, F electrons, we know that zinc, cadmium, mercury. Mercury has 4F14, uh, 5D10, 6S2 configuration, right? So F electrons have been included. So F electrons have poor shielding effect and will expose the positive charge of mercury to the H2O ligand. Okay, so they'll not be able to shield the the nucleus properly, as s electrons, they have highest shielding effect and f electrons have very poor shielding effect. So they'll expose the positive charge of mercury to the H2O ligand, and in turn what happens, see, the lone pair present on the oxygen will exhibit an inward pull. Okay, so the oxygen, the electrons of the oxygen, they will be pulled towards the, actually basically not the lone pair, it's the bond which is present, like H2O bond, if we can talk about like this. See, if we make it like this, so this is Hg 2 plus, right? So it is going to, the f electrons which are present in this mercury, they are going, this is going to pull the electrons basically from the water, right? And this bond will become weak as mercury is going to pull the electron towards itself. This oxygen will in turn, as oxygen is itself very electronegative, so this will in turn pull the electrons from the this bond, and the hydrogen atom can, sorry, H plus ion can easily leave and facilitate the removal of H plus. That is what we see the acidity. What is acidity? Acidity is basically the tendency to lose the H plus easily, right? And the conjugate base that is formed, that should be stable. That is a different thing for the organic part. But if you see this one, so the removal of H plus, if we see here, so basically the species that lose the H plus easily, they are acids, right? So that is what we have to see, the acidity of it. So this complex has the highest acidity order, even more than the C1. Okay, you can see here the order of acidity. And now if we talk about the A and B, now moving from left to right in a period. So this is iron and this is nickel. So the size is decreasing, right? Now we have seen here that smaller the size of the metal, higher the acidic character. So nickel will have more acidic character as compared to iron, right? So you can see here. That is why this trend is seen. BC, BA. This is order of the acidity. Okay. So yeah, this is enough for this one. Okay. Now this is a simple question. You can see, just for practice sake, that you need to find the oxidation state of tungsten. Okay. So this is plus 2, the magnesium, alkaline earth metal. They exist in plus 2 oxidation state. It is stable. Plus 2 X. X is the species which is tungsten, and plus 4. 4 oxygen atoms are there, and they have a charge of minus 2, right? Or 2 minus. It is 0. It doesn't have a charge. This complex doesn't have any charge on it. So that is why 0. So X will be plus 6, minus 8 plus 2 plus 6, right? So that is why the option D becomes the correct one. Okay. Yeah, this question has also been asked in GATE also, and I remember the oxidizing nature was asked in NET. Yes. So you need to see the correct order of ligand to metal charge transfer energies in the manganate, chromate, and vanadate ions. Okay. Now you can see. So if you find the oxidation state of the central metal in the given ions is, so for the A, manganese is in the plus 7 oxidation state. How do we find the oxidation state? You know that X minus 8. Why 8? Because it has a charge of minus 2. 4 into minus 2, we get minus 8 is equal to minus 1. And X minus 8 is equal to minus 1. X is equal to plus 7. Right? Similarly, for chromium, we have plus 6. And for vanadium, we have plus 5 oxidation state. Now, in this image, you can see. Now, what is the condition for the ligand to metal charge bond? Ligand should be electron rich, which is here, present here, the oxygen, oxo, O2 minus, and the metal should be electron deficient, okay, with the oxidation state greater than equal to plus 3. This is important, okay, you have to see this. So, metal should be electron deficient, okay. So, now we know that it has, this manganese has a charge of plus 7. So it is going to be it will have least energy. The electron, it is highly electronegative, and it is going to have least energy, followed by chromium and then vanadium. Okay, so yeah, if we have 2p, the this O2 minus is going to donate electrons from its 2p orbital. Okay, so these 2p is going to get this 2p, the electrons present in the 2p, they are going to get transferred to the d orbitals of manganese, chromium, and vanadium. So you can see that the most energy in the order is given here: C, D, A. Okay, yeah, this is order. Yeah, A1. So we can see that the highest energy is required for this one, the vanadium, 2p to vanadium, right? And then next is 2p to chromium, and then 2p to manganese. Okay, so the highest amount of energy that is required is for the vanadium. So that is why the ligand to metal charge transfer energies you need to find is going to be highest for the vanadium, followed by chromium, and then this manganese ion. Okay, and LMCT is very important. Color and spectra is very important from the uh, net point of view. Okay. So the intense blue color of Prussian blue is the result of. Now we need to find, these are the options: electron transfer between iron 2 and iron 1, electron transfer between iron 2 and iron 3, DD transitions, paramagnetic nature of iron 2 and iron 3. Okay. So we can see here that what happens in this Prussian blue complex. This is a Prussian blue complex, KFe, 6. So K is +1 oxidation state, Fe is in the +2 oxidation state, iron Cn6 3 minus, right? This iron is in the +3 oxidation state. So it happens intravalence charge transfer involves electron transfer from one metal in lower oxidation state to the other metal in the higher oxidation state. This is one of the charge transfer, like if you study about the LMCT, the MLCT, the metal to ligand charge transfer, ligand to metal charge transfer. So this is one of them, intravalence charge transfer. In some other complexes, PB3O4, PB3O4. Also, in this complex, also such kind of transition, the intravalence charge transfer occurs. Okay, so electron transfer takes place from iron 2 to iron 3. So it is called basically intravalence charge transfer. So electron transfer between iron 2 and iron 3. This is the correct answer. Okay. Now this is another simple question that the cis trans complexes of the type PTA2X2 are distinguished by. So these are basically distinguished by the Kerner-Pfeffer test. How you'll see it. Now we need to see here that what is the criteria of basically, yeah. So how we'll distinguish the cis and trans isomers on the basis of the Kerner-Pfeffer test. Now you'll see that this is cis. In general, it is given PT2X2, but I have taken an example here: PTNH3 whole twice Cl2 Cl2, right? So this is a cis complex. You can see Cl are here and NH3 are, they are present on the same side. Now, if we take two thiourea complexes, so not complexes, the ligand, I'm sorry, not complexes, ligand. If we take two thiourea ligands, now you can see that there is a series for the trans effect. So what is basically a trans effect? You can see here, trans effect of a ligand L promotes rapid substitution of a ligand trans to it. Trans effect of Cl minus is greater than ammonia, and also trans effect of thiourea is greater than Cl minus. That we see here. See, as mentioned in that slide, that the trans effect of Cl is greater than ammonia. Okay, so this Cl is going to kick off this ammonia, right? And this Cl is going to remove this ammonia. So we get two thiourea substituted by this NH3. Okay. Now we can see that the trans effect of thiourea is greater than Cl minus. Now thiourea is going to remove the Cl, and this thiourea is going to remove the Cl because it is in the trans position. This is what the trans effect says. So we'll get, this is the trans effect order, and on adding two ligands of thiourea, we get this platinum containing four thiourea ligands. This is for the cis case, right? Now, if we take the trans case, okay, now in this trans, you can see that now the trans effect of Cl is greater than ammonia. Now it has no option but to remove this ligand trans to it. So it will remove this Cl, and one thiourea is going to come up here, right? And now amongst all of these, the trans effect of thiourea is the highest. Now it is going to remove this Cl, and what we get is this. So this is what we get on adding thiourea to the trans complex, like PT, two NH3 ligands and two thiourea ligands, and this is what we get from the cis, from the starting from the cis. Okay, so these are different and they can be distinguished on the basis of Turner gas. Okay, now you can see the next question. Yeah. Yes, this is very important. Term symbols, microstates, they are very important from both, for both the exams. Now we need to find the term symbol of vanadium 3 plus ion. Okay. Now how do we calculate the term symbol? So um, this is what we get, L2S plus 1J, right? So this is the total angular momentum. This is a spin angular momentum, S, and J is your spin orbit coupling. What is 2s plus 1? 2s plus 1 is the spin multiplicity. So this is how a term symbol looks. Okay, this is what we have to find over here. Okay, now D2. Now for how it is D2, vanadium 3 plus, cambrium, titanium, vanadium. So it is 4s2, 3d3, right? So two electrons have been removed from 4s2 and one from D. So we get D2. D2. Now L. So this is how we make the d orbital for finding the ground state term symbol. And we need to find, like the rule is that we need to find the, for the finding the ground state term, we need to have the highest value of L. L is basically the angular momentum, total angular momentum. And also the spin multiplicity should be high, but that is not required over here. What is required, we'll see. Okay. So we have placed two electrons. Why we have placed this way, we have placed, that is why we have placed it this way, because the value of L will be highest in this way. Okay, so we will get, what do? We add up these plus 2 and plus 1, 0 minus 1 minus 2, plus 2 plus 1 we'll add up, and it is going to come up here 3, and spin is half plus half, 2 electrons are there, we get 1, S is equal to 1. Okay, and 2s plus 1, spin multiplicity 3. And what the value of J, why it is L minus S? Actually, it is from L plus S to L minus S. But we have the value of spin orbit coupling. It is from L plus S to L minus S. But we have considered L minus S because this configuration is less than half filled. Half filled, when do we get half filled? When all of these are singly occupied. Yes, but this configuration is less than half filled, so we are going to consider L minus S for the J value, right? The spin orbit coupling value. And so now L minus S, 3 minus 1 we are going to do. So this is 3, 3 minus 1 if we do, we will get 2. Okay. So L minus S will be considered for the ground state as the d orbital is less than half filled. So the ground state term symbol will be 3f2. How f we have like 3, so it is here. 2s plus 1 is 3, right? 3 it is here. 2 is basically this J value is 2. And F term, okay, when the value of total and the uh, orbital angular momentum, it is 3, we get F term. When it is 0, we get S. When it is 1, we get E. When it is 2, we get D. Okay, here it is 3, so we have the F. So this is the ground state term symbol. So basically the answer will be A. Okay, yes, this is also important question. This is also. So we assign the rate of basic hydrolysis to the following complexes. These three complexes have been given. So you need to understand a little bit about basic hydrolysis in order to solve this question. A little bit is required. So basic hydrolysis is facilitated by the presence of pi donor ligands. I'll explain this here. Cl minus is a pi donor ligand. NO2 minus and Cn minus are pi acceptor ligands. Also, minus I effect of NO2 minus is greater than Cn. En is basically this difilament. You know this. Every like this is a okay. This is En. So for the basic hydrolysis, now you can see that we have considered a complex here. Okay. If we add a base OH minus, so it is going to abstract one of the H plus from the ammonia, and we are going to get this conjugate base CONH34 NH2, because one of the H plus has gone with this NH2 minus and Ca. Okay, this is what we are going to get. Now CONH34 NH2Cl. Now this is a slow step. It will be a rate determining step for the removal of the Cl. This step only we have to see how is it facilitated by the presence of this Cl, NO2 and Cn. This we'll see in the next slide. Okay. So yeah, we were here. So this is coordination number 5. We get a PBB type, PBP, trigonal bipyramidal kind of intermediate in this case. Okay. And now this is the complete got here, and on adding water we'll get this. Okay, so water is going to give H plus 2 here, so NH3 5 and OH. Now you can see here the order of basic hydrolysis is 132. 1 is this one, this is 2, this is 3. Okay, 132. Why? Now you can see here that in the case of En, we have this En again. Now OH minus is going to abstract one of the acidic protons, H, from here. Okay, and now it is going to become NH minus. NH minus. Now it gives electron through back bonding to the cobalt. In every complex it is taking place. This is common. Okay. But now the role of these ligands play a role. Okay. Cl minus is going to act as a pi donor ligand. Actually, every ligand is a sigma donor at first. So first it is going to form a sigma bond, and it can also donate to pi. It can also donate other lone pair of electrons of itself. So that is why pi donor ligand it is. So Cl minus is going to act as a pi donor. Okay. Uh, and in these two complexes, NO2 and Cl minus, these two are pi acceptor. But obviously the electronegativity, the minus I effect of NO2 is more than Cl. So it is going to pull the electrons towards itself and will not let the Cl minus go easily. Okay. So this step, this will be the slowest amongst the basic hydrolysis. In order to facilitate the basic hydrolysis, we need to assign the order for that. So pi donor ligand, it is going to donate the electron, and the Cl minus is going to leave easily because it is receiving back bonding, and also Cl minus is acting as a pi donor. Cl, it can kick off this Cl. While if we talk about these two complexes, NO2 minus is going to pull off the electrons and will not let the Cl go. And similarly, it happens with Cn, but it occurs in the middle because of the minus side effect of NO2. Okay, so this is the order of basic hydrolysis. We need to find a rate, like basically in in the rate of basic hydrolysis. So 1, 3, and 2. 1 in this complex, uh, uh, highest will be in this one first complex, and then in this third one, last will be in the second one. Now you can see which one of the following pairs of electronic configuration of high spin transition metal ions will be in an octahedral field undergo a substantial gentler distortion. Now, okay, we need these configurations has been given, and we need to find the gentler distortion in these. So you can read it out here that according to JTB, any non-linear molecule or ion in its electronically degenerate state is unstable and undergoes some sort of distortion to lower its energy, to remove degeneracy, and to lower the symmetry. And we are talking about octahedral complexes here. Octahedral field it is given. So octahedral complexes become tetragonally distorted. You would have studied about the uh, tetragonal elongation and tetragonal compression because of the JT, right? But that is not required over here. You have to see how the distortion occurs. Strong distortion occurs in doubly degenerate state, that is when the EG orbital is unsymmetrically filled. No distortion is observed in the non-degenerate state, and weak distortion is observed for the triply degenerate state, that is when the T2G orbital is unsymmetrically filled. Now you can see that. Okay. Now for the high spin it is given, right? High spin 3D transition metal ions. Sorry, this is the configuration of the ions. This is how we do it, P2G and EG that we had seen in the earlier slide. D3 and D5, they are non-degenerate. You can see D3 and D5. Here it is symmetrically filled, right? It is symmetric, not symmetric. Yes, it is symmetric. This configuration is symmetric. T2G3, G0. Here also, 3 electrons here, 2 electrons here. It is symmetrically filled. So they are non-degenerate. Okay? They are non-degenerate. Energy of all of them is different, right? Degenerate is basically having in energy. Okay? So these are non-degenerate. D4 and D9 they are doubly degenerate. This is D4 and this is D9. How it is doubly degenerate? Because this EG, this this orbital, it is unsymmetrically filled. You can see here one is present and one there is no electron here. Similarly for D9 we have two electrons here and there is only one electron here. So it is unsymmetrically filled. So they are doubly degenerate, and this is the criteria for strong JPD, Jan distortion. And the D6 is triply degenerate. You can see this is triply degenerate because this T2G, this is unsymmetrically filled, right? Two here, one and one. So they are D4 and D9 are doubly degenerate. So you can see here that D4 and D9 are doubly degenerate. So substantial, we need to find the substantial Jankel distortion. D4 and D9 doubly degenerate, right? Strong distortion, substantial distortion. Hmm. Now the CFSC of B3 metal ions decreases in the order. Okay. Now we need to find the criteria for the CFSC. Here you can see that if you know this fact that higher the charge of the metal ion, higher will be the value of CFSC. Okay, if you know only this, you can eliminate this option A. Why? Because it has a +2 charge and these two have +3. You can eliminate. So this is what you have to do. Like eliminating the options and answering is like it helps in the exams, in the MCQ based exams. So the higher the charge on the metal ion, higher will be the value of CFS. You can see the reason also. More is the nuclear charge. Okay. More will be the repulsion between the d orbitals having electrons of the metal and the electrons of the ligand. Okay, there will be a lot of repulsion. The higher oxidation state of the metal causes the ligands to approach more closely to it, and in turn they are repelled by the electrons which are present in the d orbital. Hence, and therefore the ligands fall more spitting of the metal d orbital. So the gap between the T2G and EG increases. Okay. Next, you can see on moving down the group from 3D to 4D, chromium to molybdenum. This is chromium, molybdenum, tungsten. This is what we get. On going down the group, 3D to 4D, there occurs 30 to 40% increase in the value of CFSC. Down the group, size of the d orbital increases. Chromium, molybdenum, tungsten. Chromium is 3d5 4s1. Molybdenum is 4d5 5s1. Right? So 4d, the size of the d orbital increases, and there occurs more repulsion between the metal d electrons and the ligand electrons. Okay? And because of this repulsion again, there occurs the gap between the delta naught basically increases for molybdenum and tungsten. Chromium on moving from chromium to molybdenum to tungsten. Okay. So the answer will be C, B, and A. C, B, and A will be third option will be the correct one, right? The number of microstates. Yeah, this question is also like it is also very common. It is being asked frequently. The number of microstates for D5 electronic configuration is we need to find the microstate. Number of microstates is the number of arrangements of electrons in partially filled structures. So number of microstates is basically n factorial upon r factorial n minus r factorial. What is r? Maximum number of electrons that can be filled in a structure. So in D we can fill 10 electrons, in P we can fill 6 electrons, in S we can fill 2 electrons at max. Okay. So for D it is 10 and R is the number of given electrons. So what is R? D5. 5 is R is 5. Okay. Oh, sorry. N is 10 and R is 5. Then number of microstates will be 10 factorial upon 5 factorial, 10 minus 5 factorial, and this is what we get as the answer. So C will be your correct answer, right? Okay. So this is how you find the number of microstates. N factorial upon R factorial into N minus. You can find for any of the configurations. Okay. And this is for the number of microstates when the electronic configuration is given. And when the term is given, it is different. When suppose 3D term is given to you, suppose. Okay. Uh, 3D term is given, then the microstate formula becomes different. Okay, that is a different case. And this, when the electronic configuration is different, given, it is a different. It is this formula that we have to use. Okay, the increasing order of wavelength of absorption for the complex. Now we need to find the wavelength. You can see that chromium is in the plus 3 oxidation state in every complex. 1, 2, 3, 4. It is in the plus 3 oxidation state. So what will be the point of difference? It will be the ligand. Okay. So according to the spectrochemical series, the ligands are arranged in increasing order of their crystal field splitting power, delta naught. Yes. So in the given question, the crystal field splitting power follows the order Cn minus, ammonia, water, Cl minus. This is the energy order according to the spectrochemical series splitting order. So these Cn minus, it is a pi acceptor ligand, and these are basically these are sigma donor ligands, right? Sigma donor, and this is Cl minus is a pi donor as well. So apart from, because every ligand is a sigma donor at first. So strong ligands have high splitting strength, while weak ligands have low splitting strength. So on the basis of that only, the splitting between the T2G and EG, these have been arranged. Cn minus, NH3, H2O, Cl minus. So now we know that now you cannot put, because you can see here that what do we do like in the acidity and pK, the Ka and pK, in that we confuse and we mark the acidity, and pK has been asked. That is inverse. Ka and pK have different relation, the dissociation constant of acid and pK. Okay. Similarly here, if we can see here that 2, 3, 1, 4, we will mark the order like this for the energy. But no, it is not the order. We have the wavelength. So energy is inverse of wavelength, right? We have been asked for the wavelength. So you need to mark the wavelength, and not this will not be the correct answer. This is for the order for the energy, not the wavelength. This is for the wavelength, right? In a hurry, what do? We usually do such mistakes that we take out the order for the energy, and that is what we are going to mark. Wavelength has been given. You have to see carefully. Energy is inversely proportional to wavelength. So C will be the answer. Now, yeah, yeah, isomerism is also important from this chapter. So a complex of nickel 2 is paramagnetic, this complex. The analogous Pd2 complex is diamagnetic. We know that palladium 2 plus, palladium in the plus 2 oxidation state, palladium, platinum, they are diamagnetic, square planar. So the number of isomers that will exist for the nickel and the palladium complexes are, so these are the options. We need to find the geometrical isomers, optical isomers, and stereoisomers. So stereoisomer, for calculating the stereoisomers, this is the formula. Stereoisomers is equal to geometrical plus half of optical. S is stereoisomers, geometrical, optical. So for the nickel complex, this complex, we'll see that geometrical optic. I'll show in the next slide. I'll show it. Okay. So geometrical isomers, this is one geometrical isomer for the tetrahedral complex, and for the square planar, if we see, this is a trans and this is cis, right? So there are two geometrical isomers for the square planar, cis and trans, right? Now, if we talk about the optical, so you can see that here there is a plane of symmetry. You can see that for the tetrahedral structure, tetrahedral geometry, we have a plane here. You can pass the plane from the Cl as well for reflecting the PPH3, or you can pass the uh, mirror plane from here, and two Cl are going to reflect. So there is a plane of symmetry, and it is optically inactive, right? Similarly, when there is square planar complex, definitely there will be a molecular plane present. Square planar, all the Pd, Cl, all of them are in the same plane, and therefore it can reflect, all the atoms can reflect if we place a plane in the molecular plane. So optically inactive again. So here also the optical isomers is 0. So you can see for the nickel complex, geometrical isomer 1, optical 0. So stereoisomers will be 1 plus half into 0. Okay, optical is 0, right? Half into 0, so 1. And for the palladium complex, square planar complex, we have geometrical cis trans. Optical is again 0, and stereoisomers will be 2. So we have 1 and 2. Okay. The number of isomers that exist for molybdenum, Py3 and CSIR. Yeah, this facial meridional is also it has been asked in the exam. Facial and meridional isomers are geometrical isomers for this kind of complex. MA3D3. A3 is pyridine, fullerite, and D3 is carbonyl. Okay. All the three same ligands are present on the corner of the trigonal face of the octahedral complex in the facial isomer. So the I'll show it here. Yeah, you can see that this is your trigonal plane. Trigonal. This is how we draw it. The the octahedral geometry is there, right? This triangular part, and behind there is again a triangle, and downwards also you can do the same thing. So we have pyridine present. So this is the facial isomer. And when one pyridine is present in the another the downward trigonal face, then it will be a meridional isomer. These are geometrical isomers basically. The cis trans you can see because all of these are cis to each other, while one of the pyridine is trans, right? So now you can see here. I'll just remove this. Oh, sorry. Now you can see that if you pass a mirror plane from here, from the CO, MO, and pyridine, they are going to reflect, and similarly, this CO is going to reflect this CO. So it is optically inactive. Okay, a mirror plane is present here, so it is optically inactive. Similarly, if we pass a plane from here for the meridional, the pyridine and pyridine they are going to reflect, and it is optically inactive again. So sorry. Now geometrical is 2, geometrical, facial and meridional 2, optical 0. Both the facial and meridional isomers have plane of symmetry. Okay. So the stereo isomers will be 2, 2 plus half into 0. That will be 2. So this is what we get, number of isomers. Okay. Sorry. Now, the ground state term for this complex, the ground state term. This is also important. The Ogle diagram, these questions, they are very important from for both the exams. Basically, in Ogle diagrams, we study about the spin allowed transitions for the high spin complexes, and there is a graph that we plot between the energy, the spectroscopic term on the y-axis, while the ligand field strength on the x-axis. So basically, from the spectroscopic term only, we are going to find the ground state term for this complex. So nickel is in the +2 oxidation state. This is how you find it. Uh, so it is a D8 configuration, right? So it is a D8 configuration. So you'll fill the electrons like this, D8. Whether it is strong field, weak field, it doesn't matter over here. No, I'm talking about Ogle diagram. It is for the high spin complexes only. High spin means weak field ligand. Okay, high spin means weak field ligand for the Ogle diagram, and H2 is a weak field ligand with nickel. But what I'm talking about is D8. D8 is whatsoever way you fill the electrons, it will be in this manner only. So the ground state term for the D8 is 3F. Okay, the ground state spectroscopic term, and the molecule term symbol corresponding to 3F, we get 3. 3T1G, 3T2G, and 3A2G. I have not written the other one because it will be confusing. It is not required here, but it is given here. I'll tell you that 3F is 3A2G, right? A. Why it is A? Because it is non-degenerate. The electrons have been, it is non-degenerate. They are filled symmetrically. The electrons have been filled symmetrically. That is when we get the A term. Okay, molecule term symbol A, 3A2G. This is how we get 3A2G. Why not T and this T? T is basically triply degenerate that we had seen earlier. Triply degenerate when the T2G orbital it is unsymmetrically filled. Then we get the T term. Okay, T is T term. So T cannot be possible. It is not possible here because it is symmetrically filled. The electrons are symmetrically filled. T is when the T2G orbital is lower one. It is unsymmetrically filled. And E is also there. E is when it is doubly degenerate, and when the that is when the EG orbital is unsymmetrically filled. Okay. So for the D8 we get 3A2G. So 3A2G is your answer. C. Okay. So yeah, that is over.